Hello everyone in CIS-115. We're in the last module of the class, Module 7, and this is a short lecture on a very deep topic. The topic is recursion. Now, I'm looking at the checklist for the class here, and you can notice that you will have two true-false questions on recursion. Now, we need to make sure you understand what recursion is, and then those true-false questions could ask you something about a factorial, or they could ask you something about a loop pattern or an accumulate pattern, and you need to be able to recognize whether the recursion code is actually doing that. And they're true-false questions, and so you could actually take the code and put it into a Python program with Tawny and run it and see whether the function is actually correctly doing what they're asking. Of course, you would need to understand what the accumulate pattern is versus what the count pattern is, and so on. But there are only two true-false questions on recursion in your homework, and there will be two true-false questions on recursion in your final exam. So that's one reason to understand it. The other reason is it's really important. So let's do a program. Let's create a program with recursion in it, and we'll do it first with a loop, and then we will do the same program doing recursion. And the point I'm trying to make here is that anything that you can do with a loop, you could do with recursion. And so first, let's make a little program to calculate a factorial. So this will be calculate a factorial using a loop. Now, loops oftentimes use less memory than doing a factorial. Than doing a recursive function. But here's a function to calculate a factorial using a loop. Now, keep in mind that factorials are written, if we wanted to write factorial of 5 in math, we would write it as 5 exclamation point. And the factorial of 5 is actually 5 times 4 times 3 times 2 times 1. So if you work this out with a calculator, 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is still 120. So factorial of 5 is 120. Okay? So let's write a function to calculate a factorial doing a loop. Def, we'll call it factorial. We'll pass something in called num. It'll be our formal parameter. Total equals num. Okay? For I in range, our range would be start with num minus 1, okay? And then we would run down to 1 before 0, which would be 1. That would get us right here. We're starting here. We'll run down until we get to 1. And in order to make this work the way we've got it structured, we need to step down by 1 each time. So this would start out at 4 and then go to 3 and then go to 2, and then go to 1. And so there's my for loop, and then we'll, inside the for loop, we'll do total equals total times I. I is going to have the number in it each time the loop goes down by 1. So at the end of our function, we'll return the total. So this is kind of an accumulate pattern, isn't it? It's almost, I wanted to make sure my microphone was working properly, but so this is kind of an accumulate pattern because we're setting our total equal to something outside of the loop, and then we're doing something to our total each time through the loop. So so at the end, if we were to call this function, we could call it by just putting the function inside of a print statement, right? And we could say factorial and 5. Okay, so when this runs, 5's going to go into num. Total will get 5 in it, and then we will start out our loop at 4, and it'll run down 3, 2, 1 each time, multiplying it out. So let's see if we can get this to work in a folder here. Let's see. We'll put it in Factorial lecture. We'll call this Factorial with a loop. Okay, let's run it. Oops. Oh, I need to comment that code out. That is comments all at the top. That's not valid Python code, is it? Okay. 120. So you can see that works, and just to play with it, if we make it wanted a factorial of 6, that would be 6 times 5 times 4 times 3 times 2 times 1. If we multiplied 120 by 6, that should give us 720. So let's see if that works. 720. So a lot of times just doing a loop is easier memory-wise on the computer than doing a recursive function, but recursive functions can be much more powerful. Why would you use recursion? Well, if the program needed to change itself while it was running, it could actually rewrite itself. Think of a program that needed to learn as time goes by. It could continue to add new code to itself each time it called the function again. So let's write a recursive version of this function here that we did that's using this for loop. Now, if you look at this, if you look at what we were doing, we were basically taking the number and subtracting 1 from the number and then multiplying it by whatever was passed in. So this basically, we could do this, then do this, then do this, and then do this. So we really don't need a loop to do this. We could do this with a recursive function. And recursion is a function calling itself. So I'll put my comments that I had up here at the top, just so we still know what we're supposed to be doing. So let's do this same thing with recursion, a really, really powerful concept in the world of computers. Def factorial still looks the same right now, doesn't it? So when you're doing recursion, the first thing that you do when you get into the function, or you should do anyway, is leave yourself a way out. Because think about this for a second. If we're going to write this function named factorial, and factorial is going to call itself, it's cloning itself. It's making a copy of itself in memory over and over and over, however many times it's going to call itself. If we don't leave ourselves a way out, if we don't provide a way out, then we could effectively take every bit of memory in the computer, because each time this function calls itself, it's got to push a copy of itself onto the memory stack. So eventually we would run out of memory. Instead of having an endless loop, we would have a endless factorial until we ran out of memory. So this is my way out. That I always, when I'm doing a factorial function, the first thing I need to think about, is how am I going to get out of this? What am I going to do to leave myself a way out? So here's my way out. If num equals 0, return 1. So if we get down here and if we are sitting here and it was going to try to do this, then we just need to return 1. So that's my way out. If we get down to where num is equal to 0, then we're just going to return 1. Okay? Else, this is where we implement the recursion. Return num times factorial num minus 1. And there's a factorial function. So you notice that factorial function is calling itself. You see that, right? The name of our function is factorial. It's calling itself. So it would keep calling itself over and over and over unless we had this to make it stop. It's got to have a way to stop at some point. But each time it calls itself, it can pass something different in, couldn't it? Now, in this case, we're passing in an integer, okay? We're passing in an integer. But if you wanted to write something that actually could add code to itself, there's a Python statement. There's a Python statement called eval that will let you put code in there to run. And so we could pass code in. If we put an eval inside of our recursive function, it could keep adding code to itself each time it wanted to, learn something. So by passing, the code would obviously be a string that it was passing in. So you could do all kinds of stuff with this, but the key point is you got to have a way out. Another key point is it's calling itself. You see it, right? It's calling itself here, and here's the main function. So the function is actually calling itself. So here's the loop that we had before, and you could see that our for loop was decrementing by 1 each time through the loop. Well, here's our recursive factorial function. Which one looks simpler to you? Does this look simpler, or does the loop look simpler? So think about that. Let's go ahead and save this. Save as, we'll call this Factorial Recursive. Okay, so now let's call it and see if we get the same thing. Factorial, we were doing 5. Okay, so here we go. You can see we got 120, and remember when we were doing the loop, I tried it with 6 and we got 720. Well, let's try this one with 6, and you can see that I get 720. Okay, one interesting thing about factorials is they get really big really fast, and this is an opportunity to just show you how big of a number Python can deal with. Now these things get really big really fast, so think about all the multiplication that's going on there, but watch how big of a number this thing can actually digest here. Let's just try a factorial of 40 to begin with. See that number down there? A lot of languages will just blow before they get to something that big. Let's do something really wild. Factorial 100. Look at the number now. That's huge. I believe that we eventually run out of memory somewhere around maybe let's try 250 and see. There's a factorial of 250, that huge number. How about 350? How would you like to have to deal with that number? Okay, we haven't exhausted it yet. This ought to do it. No, it's still. So you can see that's a really huge number. This function right here had to call itself 600 times. Or it called itself 599 times, but it created 599 copies of itself in memory. You can see that all this code here got stuffed into memory. This little loop here would take a lot less memory because it's only sticking this function in memory once and then it's rolling through it. But factorials, very powerful concept. Think of how much work you could get done if you could clone yourself 600 times. So about the chapter in the book, here's the chapter in the book on recursion, and you can see that they were doing something similar to what we were doing with the factorial function. They talk about how to get the greatest common divisor using a factorial. Okay, still got an if and an else. This is their way out right here. Okay, now you can get into a situation where you need an if, an else if, and an else. 3 different things, because you see how many situations they had here. They had if n is 0, if n is 1, and otherwise. So hopefully you could see in Python this would be an if, this would be an else if, ELIF, and this would be an else. And so you can recognize the pattern right there. I'm going to skip down because that's all you've got to do on these true and false questions is see if they're implementing the pattern right. So here's a counting pattern, okay? And so it's counting. It's bumping something by 1 each time. These square brackets are an empty list, so basically this tail is taking something off of the list each time through. Here's an accumulate pattern with the list, and then here's a filtered count and a filtered accumulate pattern down here. So you'll be given some of those patterns to recognize on those 2 true-false questions. You could probably find the patterns here in the chapter material that's linked to your checklist right there, chapter on recursion. So that's a short introduction to recursion, very powerful concept. Think of it, a function cloning itself. Very, very interesting, very powerful concept. You saw how big of numbers we could deal with when we were doing this. All right, that's it for recursion. Have a good week.